So this video is going to be a continuation on our review over quadratic functions. We looked at factoring quadratic expressions, and today we're going to look at factoring quadratic expressions completely and what that means. So by definition, a polynomial is factored completely if none of the resulting factors can be factored further using integer coefficients. So to get a true idea of what this means, I want us to look at the quadratic expression 2x squared plus 6x plus 4. Now, if we were using our algebra tiles to build rectangles using those tiles, 2x squareds, 6x's, and a 4, this is one rectangle that you could build. It's an x plus 2 by 2x plus 2 rectangle. But it's not the only rectangle you could build. Here's another one. 2x plus 4 times x plus 1. Or I could build two identical rectangles that are x plus 1 times x plus 2, and I have two of them. So which of these is correct? 2x plus 2 times x plus 2, or 2x plus 4 times x plus 1, or 2 times x plus 2 times x plus 1. Now the truth is they're all factored. These are all factors of this expression 2x squared plus 6x plus 4. But which of them is true to the definition factored completely? That's going to be this third option here. This is considered factored completely because if you look at each of the factors in that product, all of them have no integer coefficients that can be factored out. It has been factored completely. Often it's easiest to remove common factors first before factoring with a generic rectangle, and this is what we're going to do for our sample problem. Alright, so let's look at one. Factor completely. Negative 5x squared plus 10x plus 15. So before we begin, we need to ask ourselves, is there a greatest common factor? And in this case, yes, there is. There's a greatest common factor of negative 5. Now, anytime that x squared term has a negative in it, it's important that we keep that in mind when we're dividing out our factors. We want to make that x squared term positive. So that's why even though the 10x and the 15 are positive, I'm going to divide out a negative 5. So to help me divide this, I put it into a rectangle for visualization. I have negative 5x squared plus 10x plus 15, and I want to divide each of those by negative 5. When I do that, I'm left with x squared minus 2x minus 3. So negative 5x squared plus 10x plus 15 is the same as negative 5 times the quantity x squared minus 2x minus 3. Now that I have that trinomial simplified, I'm going to factor what's inside the parentheses. And to do that, I'm going to use a generic rectangle and a diamond, like we did in the last video. Remembering that the ax squared term goes in one corner, and the c term goes in the other corner opposite. I multiply those two together to get the product, and I look at the b term to get the sum. So I'm looking for two factors of negative 3x squared that add to negative 2x. And between my two options here, it's going to be the first option, negative 3x and x. When I add those together, I get negative 2x. So I put them in the other corners of my generic rectangle. Then I find the greatest common factors for each partial area. X and x, positive 1 and negative 3, and I can rewrite x squared minus 2x minus 3 as the factors x plus 1 times x minus 3. Now because we're factoring this completely, and I divided out negative 5 at the beginning, I need to make sure to keep that in my answer. This negative 5 is still one of my factors. We might have factored it out earlier, but it still needs to remain in the answer. Let's try another one. Factor completely. 9x squared plus 6x minus 15. Again, ask yourself, is there a greatest common factor? Yes, 3. So I can divide out a 3 from each of these terms. 3x squared, positive 2x, negative 5. Rewriting my expression as 3 times 3x squared plus 2x minus 5. Now what's in that parentheses is what I'm going to factor now. My numbers are a lot smaller, a lot easier to work with, and we're only going to get one set of factors. So 3x squared and negative 5, I multiply them together to get negative 15x squared. but they have to add to 2x. So I'm thinking, what factors of negative 15x squared add to positive 2x? And between all of my list of factors here, the only one that's going to give me a positive 2x is negative 3x and 5x. So I'm going to put those in my missing corners of my generic rectangle. Taking out my factors of each partial area, I'm left with 3x plus 5 times x minus 1, and don't forget, times 3, because we took it out at the very beginning. Factored completely, 3 times 3x plus 5 times x minus 1. Last one, factor completely, x cubed minus 9x squared plus 14x. Now, if you look at all the coefficients, they only have a common factor of 1. But if you look at the variables, they all have at least one x in each term. So is there a greatest common factor? Yes, x. Between these three terms, I can divide out an x. And what I'm left with is x squared, negative 9x, and 14. So I'm going to take that trinomial and I'm going to factor it. Again, following the same process. X squared and 14, multiplying those two diagonals together to get 14x squared. Whatever terms I have need to add to negative 9x. So my factors of 14. Now, if I have two numbers that multiply to a positive, but add to a negative, that means that both of those numbers are going to be negative, because a negative times a negative is a positive, but a negative plus a negative is going to remain negative. So negative 7x and negative 2x is my other option. Between these two pairs of factors, negative 2x and negative 7x are going to be my terms to complete my rectangle. Taking out my common factors, I have x minus 2 and x minus 7, and don't forget the x from the beginning. We have x times x minus 2 times x minus 7, and that's how you factor an expression completely.